and then we'll be off to section 1.5. Okay, so the first one, it says estimate and classify the extrema for f of x, and we want to support our answer numerically. So remember, when we're talking about extremal points, it's points where we are decreasing and then go to increasing and then increasing back to decreasing. So just analyzing the graph, as I start on the left-hand side, you can see that I'm decreasing, decreasing, decreasing down until I hit, this would be -2. So I'm going to say roughly about a -1.5. And then I begin to increase again until I hit maybe 1.25 as a graph estimate if this is 2. So say 1.5 just to make sure. And then remember, what I'm going to do is I'm going to build a table to support this. I get my estimate graphically, but then I build a table. And this one's a multiple choice answer. So from here, we actually have enough information to make an educated guess, because here are our options. So first one says relative minimum at -1.5 and a relative maximum at 1. Okay, looking at our graph, that seems reasonable. Okay, does our table support that? Relative minimum, -1.5 is here at -9.375, -2, -9, -1, -8. So yeah, that would support a relative minimum. And with our end behavior going farther and farther towards a positive infinity, so this is, they're all higher, and -9.375 is the lowest point. So I think that could work. And then working for our relative maximum, we'd have a 1. When we plug in 1, we get 0. Okay. When I plug in 0.5, I get negative 0.875. So 0 is higher than that. When I plug in 1.5, I get a -1.125. And then when I plug in 100, I get an answer that is approaching closer and closer towards a negative infinity. So that would support it from the table. Okay, so now I believe this is going to be answer option A. Okay, and once again, with the multiple choice question, we have we're able to eliminate some answer options. Okay, that's the key. We can eliminate some answer options as we are going. Okay, here we have a parabola. Okay, once again, they're counting by 2s. So, and we're looking for our extremal points. So we're looking for points where we're decreasing and then we begin to increase. So this would only have 1. It's right here. Looks like it's roughly about a -1, maybe -0.5. A little tough to tell from the graph, but remember, I'm just grabbing an estimate because then I'm going to plug in answers close to that to build my table, and then I'll know for sure. So all of them are minimums, so I can't really eliminate one except for one. See how it says relative minimum? Okay, remember, if it's a relative and not an absolute, that would mean that there's another point on this graph that is going to be lower than that. Okay, so looking at the graph, since it's a parabola facing upwards, I know I'm going to have an absolute minimum. So I can eliminate answer option C. So now it's just kind of going through my table and knowing where my estimate was. Our graph was counting by 2 and it broke after -2 on the grid line. Okay, here's -2. And you can see that I'm clearly to the right of that. So just from my estimate, I can almost eliminate this one, and this one, but my table would confirm that. So when I plugged in -1, I got -4. When I plugged in a -0.5, I got -3.75. So -4 is less than that. And then -1.5, -3.375. So -4 is less than that as well. So I'm going to say that this is answer D. Okay, finding the average rate of change. Remember that this is based upon the slope function. Okay, where we have f of 2 or f of x2 minus f of x1 is over x2 minus x1. Okay, here they give us the interval. So we're going to have 2 be x2. Negative 1 is going to be x1. So we want to plug in 2 into our equation. Okay, so when I plug in f of 2, I get 3 times 2 cubed minus 2 squared plus 5 times 2 minus 3. So now I carry out my arithmetic. 2 cubed is 8. 2 times 2 is 4, times 2 again is 8, times 3, that's 24, minus 2 squared, which is 4, plus 5 times 2, which is 10, minus 3. So I have 24 minus 4 to make 20, plus 10 to make 30, minus 3 to make 27. 24, 20, plus 30, minus 3. Yep. Okay, so now f of negative 1. Find that. 3 times negative 1 cubed minus negative 1 squared plus 5 times negative 1 minus 3. I'm not muted again, am I? Okay, good. A little scared about since that happened the other day. So now carrying out my arithmetic, negative 1 cubed is going to be a negative 1. So 3 times negative 1 is a negative 3. Minus the quantity of negative 1 squared. Negative 1 squared is 1. So that's going to be minus 1. Plus 5 times negative 1 is a minus 5 minus 3. So negative 3 minus 1 is negative 4. Minus 5 is negative 9. Minus 12 is a negative 12. Or minus 3 is a negative 12. So now what I'm going to do is I'm going to plug these in. So f of x2 should be f of 2. So I have 27 minus a negative 12 for f of negative 1. My x2 was 2. My x1 is negative 1. So 27 minus a negative 12. That turns into a positive 39. 2 minus a negative 1 is 3. 39 and 39 thirds would simplify down to be 13, which corresponds to answer D. Okay, so whenever it's asking for the average rate of change, remember it centers around the slope formula. Okay, f of x2 minus f of x1 in the numerator over x2 minus x1. Or the simple way that we talked about it in Algebra 2 is y2 minus y1 over x2 minus x1. Just they use function notation. So we've been analyzing graphs. That's from section 1-2 through 1-4. It's all going to come together today. Now we're going to be identifying, graphing, and describing parent functions. And we're going to identify graph transformations of parent functions. Okay, transformations and translations. So most of the times, what they're going to ask is they're going to give you what g of x is. Okay, and what g of x and how it relates to the parent function. So an easy way to remember this, a times the quantity of f of x minus h minus k. Okay, so if you look, I have quite a few parentheses drawn just with function notation of f of x. Okay, this outside, this k, this is your vertical transformation. Okay, and I'm giving you this format because this simplifies making your answers helped if I didn't share, if I wasn't still sharing my screen. Okay, now you guys might be able to see it. So this is what I wrote. I wrote g of x is equal to a times the quantity of f of x minus h minus k. Okay, this k on the outside is for a vertical transformation or a vertical translation, meaning the graph is going to slide up and down. Okay, kind of like adjusting your y-intercept for a linear function. This h, okay, this is your horizontal translation. This is what makes the graph go left and right. Okay, it sets up an inside versus outside type of thing. So if I'm outside of my f of x function, I'm moving my graph up and down. Okay, if I'm inside my f of x function, I'm moving my graph left and right. Okay, and it is standard as a negative. Okay, we want to think about what makes the inside 0. Okay, so if we have a negative answer, our graph is shifted to the right. So x minus h. If it was x plus h, that means our graph is shifted to the left. Okay? And then the final one is this value of a, which is your dilation factor. Okay, it's what stretches the graph. Okay, it stretches it vertically, it compresses it vertically, and vice versa. It also compresses it horizontally if it's stretched vertically, like if you're thinking about a parabola. Parabola is normal, nice little U shape. If it's stretched vertically, it's going to be a skinny parabola. Okay, that's also known as being compressed horizontally. If it's compressed vertically, it's going to be kind of more, I don't want to say a fatter parabola, but yeah, it'd be a little bit thicker parabola. Okay, and this f of x, that corresponds to the parent function. And you're going to see all of this, and this is a pretty easy form to be able to submit our answers to, because we got to determine how many units left, how many units right did we go. But first thing we got to do is we got to talk about our parent functions. So your parent functions are the simplest forms of each function. So like x squared, x cubed. Okay, those are examples of parent functions, and you're going to see them. The constant function is a horizontal line. Okay, constant function is a horizontal line. It has no slope. The zero function is a constant function that just happens to overlap the x-axis. So it's y is equal to 0. Okay, your identity function is y is equal to x. Okay, you have quadratic function, which is all of your parabolas. So anything with x squared. You have your cubic function, which is when x is cubed. So dealing with x cubed again. You have the square root function. Okay, you have the reciprocal function. That's 1 over x. Square root function being the square root of x. The absolute value function is always expressed in the terms of absolute value. Step function and greatest integer function, those go hand in hand. Okay, that's where we're rounding to the nearest integer. Okay, and you'll see that. But the greatest integer function is a step function. It's not a continuous function. It steps up, kind of looks like a staircase. Okay, you have transformation. This is when we're transforming the graph. We're stretching it, we're compressing it. Okay, we're actually transforming the graph. Then you have translation, which is the same graph, it's just translated horizontally or translated vertically. So using H and K up there are your translations. A is your most predominant transformation. Okay, but that can also happen on the inside or outside, and you'll see that. So these are your vocab terms, and you can see most of them are just the parent functions. Okay, each one has very distinct characteristics that you will find. Oh, reflection. Okay, so reflecting it about the y-axis or the x-axis, kind of looking at it as symmetry. Dilation, we already talked about that. That's a transformation. And here we go. So here are your basic linear and polynomial parent functions. So up in the top left, we have constant function. Constant function has the form f of x is equal to c, where c is any real number, okay, and its graph is a horizontal line. So this would be like f of x is equal to 6. So it doesn't matter what x value we plug in, for f of x, we're going to get 6. Okay, what changes a constant function into a zero function is if its f of x is equal to 0. Okay, because that would be on your x-axis. So once again, very flat, very constant, never changing, and it'll continue all the way until positive infinity, all the way until negative infinity in behavior. The identity function, it sets up all of your linear functions. Okay, the identity function f of x is equal to x and passes through all points with the coordinates a. Okay, so like 1, 1, 2, 2, 3, 3, 4, 4 is what that back part's saying. This is the parent function for all of your linears. Okay, so you can see we have a slope of 1, and we don't have any, we don't have a vertical translation. If we were given the graph f of x is equal to 5x plus 5, that would be a vertical dilation. So we're adjusting the slope, so that would be increasing by 5. But we'd also be adjusting the y-intercept to shift it up 5 units. Okay, so this is the parent function for all of your linear equations. Okay, you can see passes through the origin. As x goes to a negative infinity, f of x goes to a negative infinity. As x goes to a positive infinity, f of x goes to a positive infinity. Range, all real numbers. Domain, all real numbers. This has symmetry about the origin. Okay. And its continuous function. The quadratic function, your parabola is down in the bottom left. Okay, f of x is equal to x squared and has a U-shape. Okay, parabola. You can see naturally it's an even function because it has symmetry about the y-axis. If we were to fold it in half, this side would overlap onto this side. Okay, your range, we have a minimum value. So your range is cut off, okay, depending upon where the minimum is. Our domain, all real numbers. Once again, you can dilate that by adding to A and stretching it vertically. And if A is greater than 1, it's stretched vertically. If A is less than 1, it's kind of compressed. And then you have the cubic function. F of x is equal to x cubed is symmetric about the origin. So similar to the identity function. And you can see with all of these parent functions, except for the constant function so far, they've all crossed at the origin. They all touch the point 0, 0. Okay, that's a key thing to know because that helps identify if we've shifted it up or shifted it to the right. So if we know where it's supposed to be in its basic form, we can determine what has happened to that graph. Okay, and that'll be true for all of your parent functions. They should all touch the point 0, 0. Square root function. Okay, has the form f of x is equal to the square root of x. Once again, touches the origin. Okay, you can see this range is also cut off. The domain is cut off. Okay, because we can't take the square root of a negative number and have a real number. And then the reciprocal function, it has the form of y divided f of x is equal to 1 over x. This one, instead of touching the origin, it touches the point -1, and 1, 1 to help you identify where this is translated. Okay, so 1, 1, -1, 1, -1, -1. The absolute value function, okay, denoted as f of x is equal to the absolute value of x. It's a V shape. Okay, here are some characteristics. Okay, the slope, if x is less than 0, is negative x. Okay, so that's a -1 decreasing slope. And then as soon as we get past the origin, we have a slope of 1. That's what this is saying over here. Okay, you can see that if we're using the absolute value function, we should never have a y value that's negative, because absolute value is talking about distance away from 0. So if we were to draw out a number line, -5 is 5 numbers from 0. So really talking about the 0, the distance. And that's what the example is. It says the absolute value of -5 is equal to 5. The absolute value of 0 is equal to 0. And the absolute value of 4 is equal to 4. So when you're considering absolute value, you're always thinking that you're going to have a positive. Okay, understand that with our vertical translations and horizontal translations, we can end up beneath the x-axis. Okay, but we would have to shift that graph down. So if we had f of x is equal to the absolute value of x minus 3, that graph would be shifted 3 units down. Okay, and then we would have an x-intercept at 3, 0, -3, 0, and 3, 0. Okay, but as a basics on its parent function, it should always be positive. Once again, touching the origin. Okay, so for all of your parent functions, they should cross the origin except for the reciprocal function and the constant function. Okay, and that's a helpful tip because we're going to be asked to identify what was the parent function, where did this graph slide. Here is your greatest integer function. Once again, this is your step function. Okay, this one looks intimidating. It's a little bit tough to read because we have to pay attention to where our closed dots are and where our open dots are. Believe it or not, this is still a function. This closed dot with this open dot passes the vertical line test. Okay, because we would only intercept. The key for this is that we're going to round it to the lowest integer or the lowest integer. Okay, the greatest integer function denoted as f of x is equal to, it's always expressed with double brackets, is defined as the greatest integer less than or equal to x. Okay, so for the examples, you can see -4, it got rounded to -4. 1, 2, 3, 4, that's right here. But then if we were to round a -3.5, we always round down, so that would round out to be -4. Okay, we're always rounding down until we hit the next integer. So from -4 all the way until we hit -3 in x values, they get rounded to a -4 because we're rounding down. And then as soon as we hit -3, we jump to -3. And then that continues all the way until -2, where we'd round again back down to a -3. And then once we hit -2, we'd make the jump, continue it along all the way until -1. Okay, and then -1, we hit the jump, continue that all the way around until we hit 0. Remember that 0 is an integer. And you can see it has a closed dot at the point 0, 0. So all your decimals from 0 to 0.9999999 get rounded back down to 0. Okay, this one, it's a little bit intimidating, but it's really a pretty easy function. In Desmos, the way that you would put these in, okay, this A with the brackets here, this corresponds to your absolute value function right there. Okay, you have A squared. That allows you to put an exponent in. And the cool thing about Desmos is we can just type it in. So if I wanted to go x squared, I just do that. Okay, A to the B allows you to plug in a different exponent. So if you're working with cubed, you can do it using your number pad, or you can use this to click to make 3 for x cubed. Okay, the hard one to find is the greatest integer function, which is under functions. You go to miscellaneous, and then it is floor. Okay, floor of x. And Desmos doesn't really do a good job. So you can see 1, and then as soon as I hit 2, I wish Desmos did a better job of closing and opening dots so that we could see our jumps. But you can see 1.9 gets rounded down to 1, 1.94 gets rounded down to 1. As soon as I hit 2, it bumps me up to 2. So that's how you would plug those in. And then your linear functions, oh, square root, that's the one. I knew I was forgetting one, I just didn't know which one it was. Yeah. For your square root function, okay, you can find it right here. Or since we've already covered rational exponents, you could go x to the 0.5. Okay, or you could use the simple square root right there. Just remember, if you have any horizontal translations or where x is subtracted, you would have to use parentheses if you're going to use the 0.5 in order to calculate. Okay, one of the main things we're going to do is we're going to describe characteristics of the parent functions. Okay, I believe that's like your first 4 or 5 problems. It says, describe the following characteristics of the graph of the parent function f of x is equal to 1 divided by x. And when they're talking about characteristics, they're always talking about the domain, the range, the intercepts, symmetry, continuity, and behavior, and intervals on which the graph is increasing or decreasing. So basically really summarizing everything that we've covered so far. So the good news is a lot of this we can get from just analyzing the graph. So here they have a graph. Okay, it has the following characteristics. If we're looking at it, our domain and range is kind of cut off. X and Y are never equal to 0. Okay, because if we have a 0 for an X, we're undefined. Okay, and it doesn't matter how far or how far away from 0 we get, we'll never truly hit 0 because we have the 1 in the numerator. The domain of the function is from negative infinity to 0 with a union between 0 and positive infinity. And the range is the exact same. Okay, from negative infinity to 0, union 0, positive infinity. So again, it's just from the nature of it. If we plug a 0 in for x, we become undefined. And because we have a 1 in the numerator, we can never truly get 0. 1 divided by 1,000,000 is still 1,000,000th, which is greater than 0. So since we can't touch 0, that means this graph has no intercepts. Okay, it doesn't cross the x-axis, it doesn't cross the y-axis at all. Okay, the graph is symmetric with respect to the origin. Okay, remember that is if we were to take the opposite of both the y and the x value. So if we were using with 0.11 here, if we were to take the opposite of both the y and the x, would we fall on the graph? And the answer to that is yes. okay, because we would go from 1, 1 to -1, -1. Okay, the graph is continuous for all values in its domain with an infinite discontinuity at x equals 0. That's because the limit as we approach 0 from both sides gets farther and farther apart. And the end behavior, as x approaches -infinity, f of x approaches 0. Okay, it gets closer and closer to 0, but it never touches it. And then as x goes to a positive infinity, f of x also approaches 0. So you can see it has what's known as a horizontal asymptote and a vertical asymptote. Okay, we're going to get very, very close, but we can never touch those. The graph is decreasing on the interval from -infinity to 0 and decreasing from 0 to a positive infinity. Okay, so once again, that's simply put, as we move left to right, our graph continues to go down, but then we hit our asymptote. So we have to start back up here, and then we continue to go down as we move left to right. So all of those characteristics broken down are our answer. Okay, so it's a lot of language in this section. It's not necessarily the hardest section, but it's a lot of language to it because we're analyzing the graphs. Okay, so describing the parent, the characteristics of the graph of the parent function x squared. So domain-wise, we know domain is going to be all real numbers. Okay, because we can always plug in. The range, it's going to be limited. It's going to be limited. It's going to have a minimum value, and in this case, it's going to be 0. So our range is 0 to positive infinity. The x and y intercepts, once again, it's a parent function. So it crosses both the x and y axis at 0, 0. This one is going to have y-axis symmetry. Okay, that's because if we plug in, if we have the value x and we plug in -x, we would get the same y value. Our continuity is continuous in behavior since it's a parabola going up. As x approaches positive infinity, f of x approaches positive infinity. The intervals on which the graph is increasing or decreasing, it's decreasing from -infinity to 0, and it's increasing from 0 to positive infinity. And once again, you can see those pretty good just from the graph of x squared. Okay, vertical and horizontal translations. This is what I was talking about when we were using this g of x equation that I put onto the board. So the graph of g of x is equal to f of x plus k. This is the graph of f of x translated k units up when k is positive and k units down when k is negative. So outside. Outside is your vertical and translations. Okay, the graph of g of x is equal to f of x minus h is the graph of f of x translated h units right when h is greater than 0 and h units left when h is less than 0. Okay, so you can see it's naturally a negative number or it's naturally subtraction. So that means that h is positive in this case. That means we're shifting to the right if it's negative. We shift to the left if it's addition. Okay, so that sets up your inside-outside. Okay, it makes it fairly easy and fairly to write equations for our transformations. If we remember, outside is vertical, inside is horizontal. Okay, so use the graph of f of x, which is equal to x cubed, to graph the function x cubed minus 2. So here we got to ask ourselves, is this outside or inside? Okay, x cubed is our f of x. So this would mean that this isn't outside. Okay, it would be inside if it looked like this. They use g of x. Yep. G of x is equal to x minus 2 cubed. This would be your horizontal. But the way that they've given it to us is like this. And you can even put the parentheses if you want to help yourself. Okay? So vertical translation. So it's just the parent graph of x cubed shifted down 2. Okay, so instead of crossing at the origin, we cross at 0, -2. And all of our other function values would correlate from that. Okay, once again, they will put parentheses if they're talking about a horizontal translation. So, but in this case, it's on the outside, so we know that it's a vertical translation. Okay, and that's what g of x looks like as it compares to f of x. Okay, use the graph of f of x, which is equal to x cubed, to graph the function g of x, which is equal to x minus 1 cubed. So here, this is inside, so we're thinking horizontal translation. It's not stretched, it's not doing anything like that, so it's not transformed. Still that graph, it's just shifted 1 unit to the right. Okay, and the way that I think about whether it goes left and right, to help myself remember, I ask myself, what would make the inside of these parentheses 0? Right? And the answer to that would be 1. So when I plug in 1, I get 1 minus 1 cubed, which is equal to 0. Okay, use the graph of f of x is equal to x cubed to graph the function x minus 1 cubed minus 2. So this is combining them both. This graph is shifted to the right 1 because the inside value to make it 0 is 1. So it's shifted to the right 1, and then it's shifted down 2. Okay, we have the graph x squared, and we want to find g of x, which is equal to x minus 2 squared minus 1. So this graph should be shifted to the right 2, down 1, which corresponds to answer B. Okay, reflections on the coordinates of axes. We're flipping it over the x-axis or over the y-axis. Once again, looking inside, outside. So to the right here, or to the left, we have g of x is equal to a negative f of x. Is the graph of f of x reflected about the x-axis. You can remember this when we were talking about parabolas in Algebra 2, that when we have a negative a value, the parabola points down. That's just a reflection about the x-axis, okay, the negative a value. Okay, in reflection about the y-axis is when it's on the inside. So g of x is equal to f of a negative x. Is the graph of f of x reflected in the y-axis? So it takes it from the right to the left. So inside, y-axis, outside, x-axis. Okay, write equations for transformations. Describe how the graphs of f of x, which is equal to the square root of x, and g of x are related. Then write an equation for g of x. So our parent function is the square root of x, okay, and it looks like it's been shifted up 1. So using our inside outside, this is a vertical translation of 1 unit. So it would be g of x is equal to the square root of x plus 1. And we got to be very careful about where or how we write this. Understand that this is outside. If it was the square root of x plus 1 and the 1 was under the square root symbol, that would be considered inside, talking about a horizontal translation. Okay, describe how the graphs of f of x is equal to the square root of x and g of x are related. Then write an equation for g of x. So first, let's talk about our translation. This graph should start at the origin for the parent function. Okay, looking at it, it doesn't start on the parent function. So it's been shifted to the left one. So we know on the inside, it has to be the square root of x plus 1. But then we have a reflection over the x-axis, which corresponds to a negative on the outside. So g of x should be equal to the negative square root of x plus 1. Okay, describe how the graphs of f of x cubed, f of x, which is equal to x cubed, and g of x are related. Then write the equation for g of x. So we have f of x here. Okay, it doesn't look like it's been stretched at all. It just looks like it's been shifted down 3 units. So we want to find the outside, which would be b. Okay, vertical and horizontal translations. This corresponds to your value of A, that dilation factor. Okay, the dilation can happen on the inside or the outside. Just in all reality, it's the same thing. It's really essentially the same thing because if you're expanding it vertically and you're compressing it horizontally, there's a chance you're going to overlap. So on the left side is when A is on the outside. So g of x is equal to A times f of x. The graph is expanded vertically if A is greater than 1. Okay, and that's any integer greater than 1. So it's a skinny parabola. That's what I was talking about, skinny parabola. When A is between 0 and 1, you can see that it's kind of been smushed down. Okay, or a fatter parabola. Horizontal, same exact thing. If A is greater than 1, we're stretching it vertically or we're compressing it horizontally. And then if A is between 0 and 1, once again, we're stretching it vertically or compressing it vertically. So these two run hand in hand. The key being, pay attention to the absolute value of A. If it's greater than 1, it's stretched vertically. If it's between 0 and 1, it's compressed vertically. Okay, so identify the parent function of f of x, which g of x. So we have 3 divided by x, and how are these graphs? This is the reciprocal function, right? Describe how the graphs of g of x and f of x are related, then graph f of x and g of x on the same axes. This is the parent, the reciprocal function is the parent function. So f of x is equal to 1 divided by x. And if you look, this is going to be a vertical stretching, okay, where we multiplied it by 3. So instead of crossing over the points, instead of crossing through the points 1, 1, and negative 1, negative 1, we're going to cross through the points, it should be 3, negative 1. Okay, so you can see this impact has been stretched vertically. Okay, identify the parent function of f of x, which is equal to g of x. That's the negative absolute value of 4x. So the parent function is the absolute value function, absolute value of x. Okay, this is on the inside. This is on the inside, so this has been compressed horizontally by a factor of 4, or it's been stretched vertically by a factor of 4. Okay, I forgot the negative, which flips it over the x-axis because the negative's on the outside. And that's what it would look like. Okay, I know I'm going fast. I'm trying to because I only got 8 minutes left. Okay, so identify the parent function of f of x and g of x. So the parent function is going to be x cubed. Okay, the cubic function. This is an inside function. Okay, so this is going to be compressed. This is going to be stretched horizontally. Okay, graphing a piecewise function. Okay, this is probably one of the harder areas, but it's the last example that I have for you. Okay, and the key is we want to pay attention to where this domain is. Okay, it's this function, but it's limited by the domain. So anytime x is negative, okay, we're going to be using the graph x plus the absolute value of x plus 2. Okay, and then when it's between a 0 and a positive 2, we're going to be using the absolute value of x minus 2. Okay, it's piecewise functions aren't very difficult. It's just we got to know where our domain is. Okay, and another thing to realize is that this portion of this piecewise function is going to have an open circle at the x value of 0 because that is not included. Okay, it's not included. It's not less than or equal to. Here is our closed circle on 0. Okay, because x can be greater than or equal to 0. We're going to have a closed circle on 2 for this middle portion. And then we're going to have an open circle on 2 and for all x values that are greater. Okay, and when we do this, we're going to be left with this. So on the interval from negative infinity to 0, we're graphing y is equal to the absolute value of x plus 2. Absolute value function just shifted to the left twice. So interval from 0 to 2, we're graphing the absolute value of x minus 2. And the interval from 2 to infinity, we're graphing y is equal to the square root of x minus 2 plus 2. Okay, and there they're talking about the circles. Okay, once again, because not included. On our top one, 0 is not included. Our middle one encompasses both 2 and 0. And then our bottom one, 2, is not included in the domain. Okay, and that's what our piecewise function looks like. This is our top portion here with the open circle at 0. Here is our middle portion. And here is our bottom portion. Okay, and that's what I have for you. I got 5 minutes to answer questions if you want to put them in the chat. Or you can shoot me an email as well. I'm doing pretty good responding to questions, I feel like, but you guys also don't ask a whole lot of questions. So I don't know if I'm just killing it when it comes to lectures or if we're being shy and not wanting to ask questions.